You might be interested to know that I actually work with RF equipment professionally, and one of the things that means is that I have access to a spectrum analyzer. This spectrum analyzer is optimized for Wi-Fi analysis, and so it works in the 2.4 and 5 gigahertz bands. And if you were to compare the frequencies I have here to the frequencies on your FPV chart, you would see that I don't quite have the exact same. The FPV frequencies are a little bit below and a little bit above what my spectrum analyzer records. But I still think there's a lot of opportunity here to take a look at what some of the FPV equipment we work with looks like when we actually transmit in the air with a spectrum analyzer. So I'm recording my spectrum analyzer here, and I've got the frequencies here, and then this is 5 gigahertz band recording there. And I've also got my LCD screen with a DVR recording, so I can cut to the what you would be seeing in the goggles if that becomes relevant. And what I'm going to do right now is I've got my transmitter set on 5800, so that's Fat Shark band F, channel 4, or is it? I think I've actually got it on 5820. My mistake. And I'm going to take the copter across the room so it's not right up next to the spectrum analyzer just shouting in its ear, and I'm going to plug it in. So hang on while I do that. Telemetry recovered. Okay. Now, actually, I got to set the channel on my DVR. There we go. Okay, DVR is now recording on the right channel. And then because there's oftentimes a lot of little blips when something first turns on, I'm just going to reset this max hold. And we can take a look at what we get here. And I'll just give a second for that to populate. Okay, so now we've got fairly good population here. Notice that the spectrum analyzer has identified wireless video camera, so it's identified the device, very clever. And it's showing that on this channel there is 96% duty cycle. Hold on a second. Thank you, Tyrannus. All right, I have to go shut up my Tyrannus. You can see that it's showing 96% duty cycle. So this is basically a continuous transmission as opposed to something like a Wi-Fi access point where it's a digital transmission where it would only transmit when it actually had data to send. So you see these little blips here, but if we look down in the spectrogram graph, we can see that they're very, very short in nature, and that something in my house is occasionally coming up to the 5 gigahertz band, sending a tiny burst of data and then leaving. So don't pay any attention to this here. But this here, this is my video transmitter on frequency 5820. So here's our center frequency, 5820. And we can see the strength of the data here. We can start to see why we need spacing between these channels. We can see that the 5820 is where the data is peaking. And if we can see it almost better in the spectrogram here, we can see from about 5815 to 5825, right? So that's about 10 megahertz. We have this peak of data, and then it goes down somewhat from about here to here. And then let's see, this is negative 40, that's about negative 50 dBm here. Oh, we can actually see it, yeah, negative 50. And as we come down here, we're down to about negative 80 dBm. So that's about 30 dB of attenuation there. And at that point, so I would say the edge of the channel is probably right about here. Yeah, right about here. And that's probably about how much separation you need. And if I'm really clever, then that's going to coincidentally turn out to be about 40 megahertz, because 40 megahertz is the standard for how much spacing you want. Now, I'm going to take the copter and I'm going to move it closer to the receiver. Now, this is not going to make any difference at all in the video quality, because the way RF works is when you have enough signal strength or signal to noise ratio, when you have enough, more doesn't make a difference, really. It's gone from perfect to even perfecter. Doesn't matter, right? So I'm going to move it closer, and I want you to watch what happens here and down in the spectrogram. Did you see what happened? Okay. Now notice that when I did that, not only the whole thing shifted up. So whereas our peak used to be at about -50, now this low spot is it's at -40. That's even more. Okay. So distance matters a lot. I mean, distance matters a lot in terms of how much interference you're going to get. One takeaway there is this sort of gives you a perspective on why you can have two copters powered up and they can be fine when they're sitting next to their receiver. So you power up your copter on the table and you're sitting right next to it with your goggles on, it looks fine. Somebody else powers up across the room, everybody feels fine. But then as you start flying away, you both suddenly black out and realize you're stomping on each other. Because when you're up close to your own receiver, you're in this sort of red hot band. When you fly away, it gets weaker and you stomp on each other. The other thing you can see is that in this section here, this green area, like this green area is roughly here. So say that's at about -65. Notice that when I brought the transmitter close to the receiver, basically the whole band just got blasted out to -65-ish. And that's why if somebody powers up close enough to you, it doesn't matter what channel they're on, they can knock you off. If they're standing right next to you with their copter and they power it up and their transmitter is right near your goggles, they can knock you off. It's no good. Okay, so now the next thing I'm going to do is this is a 250 milliwatt transmitter, by the way. I have another transmitter. It so happens to be a 600 milliwatt transmitter. Let me pause here and set the channel for it real quick, and I'll be back in a second. Okay, now I have the 600 milliwatt transmitter turned on, and I believe it is on channel 5740. That does look right. That does appear to be where the center frequency is here. And just for your perspective, I'm going to go ahead and take it and put it right next to the copter. So they're both equidistant. They're both equidistant from the spectrum analyzer. And then just to make sure everything is fair, I'm going to reset this. Now it is interesting that the shape of the spectral pattern here is a little different. Bear in mind that this one has a linear polarized antenna on it. I actually broke my last circular polarized antenna. And this one has a circular polarized antenna on it. The spectrum analyzer, of course, has a linear polarized antenna. I don't think that would change the spectral shape like you're seeing here, but I don't know because I don't work with circular polarized stuff in my job very much. The other thing that I think is worth seeing is, yeah, the peak is very different. The peak is they're peaking at kind of the same height, but the shape is very different. It's very interesting. And I would be very interested to see what happens if I bring that 600 milliwatt transmitter right over here next to the spectrum analyzer. See what happens to the video and to the trace. Okay. Here I go. Now the good news is that they are far enough apart that the video is not breaking up at all. So that's good news. Video is not breaking up at all. You can see, however, the difference in the noise floor that has occurred on the spectral trace. And you can see that if they were not this far apart, they could begin to interfere. Right now we've got one on 5740 and one on 5820. That is plenty of separation. But if you imagine that we squeeze these closer together, they certainly could begin to interfere. So now, instead of having my copter on the other side of the room, 10 feet away, I've taken it all the way to the other side of the floor, and I also put it right next to my furnace. which is a big metal box, of course. And the net effect, as you can see, is that the signal has gotten a lot weaker. Instead of a peak of around -45, we've got a peak of closer to -65, let's say. Now that's still a plenty usable signal, and in fact, if you look at my DVR, you'll see that I've got a perfectly clean video. But I'm wondering if now that it's weaker, I can induce more interference in the video with this 600 milliwatt transmitter, bringing it right close to the receiver. Let's find out. Okay, here it comes. And now I'm going to bring it right close to the receiver and see if I get any breakup. And I am getting just the tiniest bit of breakup, but really not much. Just, yeah, there it is. Now, to be completely fair, it's really, oh, there we go. It's like 3 inches away. But the signal is breaking up. And I'll show you that. I'll put an inset there. And you can see how hang on, I'm juggling a plane here. You can see how the entire spectrum is being wiped out by this 600 milliwatt transmitter when it gets close enough to the receiver. Now that's being exacerbated because it's 600 milliwatts. It would be slightly better if it was 250. But look over here. You see how my video is just gone? It's just gone. Okay, and I'm going to power that down now. And everything should come back. There we go. So the takeaway from this is that this whole idea of the spacing on the channels is very dependent on your output transmit power level and your proximity. That spacing between the pilots, physical spacing between the pilots, is just as important as frequency spacing. We don't want to fly your copter over near somebody else's goggles. You don't want to put your transmitter near somebody else's receiver if you can possibly avoid it. Granted, we didn't start to see problems until we were like 3 inches away, but at the same time, we had plenty of frequency separation here. If one was on, say, 5820 and the other was on, say, 5800, we would see breakups much sooner, even though they nominally have, well, that's only 20 megahertz. We really want at least 40 megahertz. So 5820 to 5780, right? We would see breakup sooner because they were closer together on frequency space. Alrighty, well, good. I hope you enjoyed that, and as always, happy flying.